Alright, so today I'm gonna be explaining this important paper with the title Node Mutual Information, Enhancing Graph Neural Networks for Heterophily. So this is Norip's paper in 2023. Graph neural networks have achieved great success in graph analysis by leveraging homophily, where connected nodes share similar properties. However, GNNs struggle on heterophilic graphs, where connected nodes tend to differ. Some of the existing methods use neighborhood expansion mechanism, which is intractable for large graphs. And this paper proposes utilizing node mutual information to capture dependencies between nodes in heterophilic graphs for use in GNNs. We first define a probability space associated with the graph and introduce kth node random variables to partition the graph based on node distances. The mutual information between two nodes, random variables, then quantifies their dependency regardless of distance by considering both direct and indirect connections. We propose case MIGNN, where the case mutual information values are used as weights in message aggregation function. So you got the idea. They are just weights in the message aggregation function. This is the idea of this paper. So you see in figure that the input graph is given with a set of nodes and a set of edges. Node random variables are defined according to K. The zeroth node variable of V only separates V itself from the rest of the nodes. On the other hand, the first node random variable of V divides the nodes in the graph into V, its one hop neighbors, and the rest of the nodes. And in C, here you see the two nodes random variables. We generate different joint probability distributions. Because one of them can give 0, here the other one can be 1. 1, 0, 1, 1, different combination. And finally, in D, this is how the node mutual information induced by the case node random variable allows us to measure dependency between two random variables. So it can be used in GNNs as edge weight. So just like in the past 8 videos, we talked about these homophily measures. Like this one, the ratio of nodes that share the same class among adjacent nodes. Also for the edge. And but class homophily evaluates homophily at the class level here, regardless of class imbalance. However, those homophily in the same graphs can vary. So they define adjusted version of their homophily. And you know about mutual information between two random variables. So here they define a probability space associated with graph. A probability space is just a triple. And D here is just the outgoing degree of V. Then they define case node random variable associated to V. Then they define case entropy of a node, which case J's entropy of two nodes. So these two definitions. So you see 6 different examples. You see comparison of node similarity for examples. We have mutual information, Now, what can we do with these node similarities? So preferential attachment is a measure of similarity that based on the idea that nodes with more connections are more likely to be connected to other nodes. However, it does not consider the number of common neighbors or the structural configuration of the subgraph. Also, Adamic ADAR and resource allocation are more sophisticated measures of similarity that take into account the number of common neighbors and the structural configuration of the subgraph. However, they still not as accurate as mutual information. So we stick to mutual information. So they define this node mutual information message passing. So it's just a weighted version of what you know. Of course, they still have the weight for learning, but it is weighted with mutual information as well. And they did experiments on squirrel, chamelson, which are very difficult. They compared GCN with their method.